what I want to finish up with is the idea of what sort of things do we do with partial differential equations. And this is a topic that obviously it could be an entire class in itself, and it really should be. It's one of those math classes that it's not really bad to take. It can be helpful. In the math class, they would do a lot more theory and theorems and proofs of stuff, more than what we would do. The other big thing to keep in mind is we're often just abbreviate it Pde because that's shorter and easier. And it's important to kind of contrast a little bit why we would use ordinary differential equations, ODEs versus PDEs. And it should be somewhat obvious to you, but the fundamental difference, really from a physics point of view, is almost all of our ODEs are in time. They're dynamics equations. They're fundamentally, we're looking at pure time dependence. You know, the classic in physics is F equals ma, where we're dealing with the time dependence of position. But you can also think of chemical reactions, where you're just considering basic rate equation. You can think of population dynamics, where again, you're thinking of it as population dynamics in time. The one other place the ordinary differential equation will come up is if you're just looking at a one-dimensional system. Because then, of course, you have only one spatial derivative, and we might as well call it x, d by dx. But what's really important in most physical situations is not simply the dynamics, and also not simply one spatial dynamic. If we think about our classic two that I mentioned, chemical reactions and population dynamics, if I have a chemical reaction, even if all I care about is the behavior in time, for two chemicals to react, they need to be in the same spot. Ultimately, space might matter. And again, if you're thinking about anything where we start working with fields, electric fields, magnetic fields, light, density fields, velocity fields, anything spread out in space, any continuum, then the spatial degrees of freedom are relevant for the dynamical degrees of freedom. And we're going to couple space and time. And even if you have only one dimension in space, if you have one dimension in space coupled with time, you get partial derivatives. You have the dependence in space and the dependence in time. Occasionally, you will be looking at the steady state or non-time dependent behavior of a full three-dimensional, two-dimensional system. And then you still have a partial differential equation, because you need to worry about both the x and y, or both x, y, and z coordinates. And so it's a good idea to know what are the common PDEs that show up in physics. Anyone think of a few? Wave equations 1. I'm going to write them down in a particular order, but just let you guys. Well, heat equation. So mass and fluid transport. What else? Well, one of the most basic first ones that we deal with only involves space, and it's Laplace's equation. Anyone remember what that one is? It's close. It's del squared of u equals 0. So not just a gradient. This one's very interesting. I mean, it comes in E and M for the cases where we have no charge, because del dot E is 0, and E is the gradient of phi. And when you put those two together, that tells me del squared phi equals 0. So it's a common equation to solve. It also shows up in fluid dynamics. It shows up in a lot of cases. Mathematically, it's a very interesting equation. And what's most interesting about it is everything is set by the boundaries. Okay? And so for steady state non-changing boundaries, a lot's known. It's pretty easy. You can just put it on most numerical solvers if the boundaries are kind of weird and strange and get a solution right away. But there's a lot of cases where the boundaries are actually moving, particularly in fluid dynamics applications, and where there's interesting things, and that's still some major mathematical puzzles, and it's a very, very interesting case when you're doing that. Now, there's a simple modification of this, often called Poisson's equation, which basically refers to the case when you would have a charge density. And so that's simply del squared u equals some function of x, y, and z. So it's the difference between the homogeneous and the inhomogeneous version. And so now you have some source in your del squared u, and that's a little more challenging to do. Okay. Staying in the realm of non-time dependence, one other tends to get a name, the Helmholtz equation, which is related to this. Shows up in heat examples and such. And the difference is, notice that you're really looking at the behavior around now a non-zero wave vector. Right? If I think of this as a linear operator, I can write this del squared plus k squared acting on f equals 0. So it's almost the same as the Laplace equation, del squared f equals 0. It's almost similar to Poisson, but it's not a function over here. It's just k squared times f itself. It's kind of like putting in the harmonic oscillator where you have the d squared dx squared equals minus k squared x. So you have a built-in natural frequency. It's like having a natural wavelength here. And we look at these things. We would often call this as a propagator. And you might, instead of k here, for instance, have mass. So you might, in certain applications, be doing del squared plus m squared, f equals 0. And it would be the difference between a particle with mass and del squared f equals 0, a particle without mass. Okay, so the k squared can have very physical meanings depending on the situation. The other three biggies we already mentioned. Instead of heat, I'll just call it the diffusion equation. What is the key feature of an equation that makes it diffusive or diffusion? Well, that's the physical behavior you get out of it. As an equation, when I look at this, how would I know right away that this is a diffusion equation? It looks like that, but you'll see I'm going to write the wave equation the same way to fool you. But that is a good thing to look at. That was not bad. How do you know this is a diffusion equation, not a wave equation? How would you describe this to someone if you had to be telling them what the order of this equation is? Well, it's first order in time, second order in space. The orders are different, and that's what makes it a diffusion equation. So it's second order in space and first order in time. That's the key piece. We're going to come back to that in a little bit in a different section to show that. But it's really this difference in how time and space evolve that leads to the diffusion behavior. And we contrast that with the wave equation, which is del squared u equals 1 over v squared d squared u dt squared. And now you see they're both second order. And if we think about this, what is the fundamental form that I can write a wave in? What's our fundamental thing that we try and do when we write a wave? Well, we tend to use sines and cosines, but what defines a wave? Right? It doesn't have to be a periodic wave. We always write it as a function of what? In what way? It's just not any arbitrary function of x and t. Well, they come as a group, right? It comes as kx plus or minus omega t. That's what makes it that wave behavior that moves, right? As I increase t, x must decrease if it's the plus. If I increase t, x increases if it's the minus, and I get my left and right traveling waves. This is kind of my fundamental wave thing. And notice, for them to come paired in as a variable, it makes sense that the derivatives have to have the same order, or it would be a little weird. And that particularly makes sense when we think about the prototypical wave, which is e to the I kx plus or minus omega t. We'll come back to this. The key thing about this e to the I kx plus or minus t format is keep in mind that is not a real number, right? So that's not going to be a real wave. At the end of the day, if I want to draw a wave, I can't draw e to the I kx. It's some imaginary thing. I can draw the real part of it, which is a cosine kx plus or minus t. I can draw the imaginary part of it. But as we've learned over and over now, e to the I kx plus or minus omega t is the best way to keep track of phases. It's the best way to do things when things are linear, because the real and imaginary don't get mixed. And so I can really think of this as my wave, and then at the end of the day, take the real or imaginary part. Now, I can have the occasional case, I'm not going to write it down, where it's first order in space and first order in time. That'll still give me a wave, because it's the same order that matters. It's not the second order that's key. Now, the third one we want to look at is the Schrodinger equation for quantum mechanics. Hopefully most of you saw this as a wave equation already. And if I write it down, for psi, this is what I get. What order is this in space? What order is it in time? First. So why do I call this a wave equation? We just said that second order in space, first order in time is a diffusion equation. Why is this a wave equation? No, it's not the potential energy that does it to you. It's a concept that we've used multiple times in this course.
Oh, because we have the I.
And what does the I do?
Phase shifted 90.
It's a phase shifted 90.
Converse to the other.
Sine to cosine. Or if I'm thinking in terms of e to the I kx plus or minus omega t, what do i's do?
Make the real part imaginary.
Well, it does that, but, or I should say this, what does the d by dt do? It brings down an I. So this is like having another time derivative. It's not exactly the same, but it's enough like it that this turns it into a wave equation. And that's kind of the key feature there, is that I is fundamental. Keep in mind, why do we have an I d by dt, not just d by dt here? This is another big idea from the class. Why do I have an I d by dt? Why can't I just have d by dt here if I'm doing quantum mechanics? Why do I know there needs to be an I there? The operator needs to be Hermitian, and we saw that from differential operators, d by dt was not Hermitian. I d by dt was, because when I integrate by parts, I pick up a minus sign, and when I do the complex conjugate, I get rid of the minus sign. So the I d by dt is absolutely critical, because that's what makes it Hermitian. The second order one was already Hermitian by itself, because doing two derivatives twice, integration by parts gets rid of the minus sign. So this really is using a lot of the ideas we've had already in the course. Now, these were all linear. It is worth mentioning something we won't do anything with in this class, is nonlinear PDEs are very important. There's lots of techniques associated with them. They're really fundamentally one of the things that you use in pattern formation, non-equilibrium physics, nonlinear dynamics. The most common to use is the Navier-Stokes equation. And what we have basically here is this turns out to be essentially ma, the acceleration. And here's the nonlinear part. And physically, we get a v dot grad v, because if I want to know how things change in time, they can either change in time where they are, or they can change in time by moving to a new space if there's a gradient. Right? So if I move to a new spot in space and my velocity is changing with space, then I've changed my velocity in time. And so that's why this structure shows up. And then this is F equals ma, so I get forces from pressures and from viscosities. And this is basically viscosity. So this is the Navier-Stokes equation. Again, we're not going to really do anything with it, but I've got a term with v dot v in it. So that's a nonlinear term. Notice that's very different than what will happen in quantum mechanics. V of x might be something like 1/2 kx squared, a harmonic oscillator. This does not make it nonlinear. Why? X squared is nonlinear. Why does this not make the equation nonlinear? That's not the problem. That can still make it nonlinear. What?
With respect to time?
That doesn't matter. What makes something nonlinear? What do I care about? The behavior of the thing I am solving for. Solving for. Am I solving for x? No, what am I solving for here? Psi of x. Psi is still only in the equation linearly. So it doesn't matter what the power of the coefficient of psi is. That doesn't make it nonlinear. And that's very important and often a confusing feature. In this case, I am solving for velocity. And that is why this equation is nonlinear. And that's key. So things like the del squared v don't matter. The other way it can end up being nonlinear is if your viscosity depends on velocity. That sometimes happens. Now, the last piece to this little introduction, basically, even from a math point of view, but really from a physics point of view, what we want to look for when we think about solving PDEs is this, even more than ODEs, which we talked about it, is you will often know the solution ahead of time. Someone else has solved them because they are such standard equations and they've shown up so much. But what you are looking at is an interesting boundary value problem. That's particularly true for, say, something like del squared u equals 0. Very well understood equation from its possible solutions, but lots of interesting boundaries you can imagine having to deal with, particularly in electrostatics, as you make different shapes and things like that. So it's the boundary values that are often the interesting thing, which is related to the geometry and the symmetry, which really tells you what coordinate system you're going to do. This is why understanding spherical and cylindrical coordinates really becomes key, because it's most likely a PDE that you're going to end up doing the spherical or cylindrical coordinates in, because if it's a spherical symmetric situation, you use spherical coordinates and maybe you only have to solve the radial equation and things like that. So that really is helpful, particularly if you're trying to do it analytically. The final, one of the other pieces is, because you know the solution, you're almost always thinking in terms of the phrase normal modes, which is what we used to call eigenfunctions. For all the linear equations, you're really going to be ultimately doing linear superposition of known solutions. And if you have a complete set of solutions that are a basis, which we know are eigenfunctions of a Hermitian operator, form a basis, and it's an orthogonal basis, then we can do our expansion. And that's really what we mean by normal mode. And so really what you're doing is taking your eigenfunctions and writing them down and doing something interesting with it. One thing we will not talk about is Green's functions. That's the way of thinking of what would the response to a delta function be. And a delta function, if you think about it, remember one of our bases for space was to just give the value of the function everywhere in space. right? That's an infinite basis that works. If I tell you the function everywhere in space, I've got a basis. Delta functions allow me to do that, right? If I integrate over a delta function at all points in space, I'm summing over all points in space. So if I know the solution for a delta function, I can find the solution for any arbitrary function. And so that's kind of the idea behind Green's functions. It's not something we're going to do, but just kind of preparing you when you see them later. The physical idea behind a Green's function is pretty much no different than what we're doing with our other eigenfunctions, except use delta functions and sum over those at all points in space. And then finally, most of the time, any real new situation, you're going to be doing it numerically. It's new because all the analytic ones have been done. And you want to learn your numerical techniques. So that's where we're going to be going with this.